Hello, Year 13, and welcome to our first lesson of the new module, and it's on acids and bases. This is something of a refresher, and a couple of new ideas are going to be introduced, but it's very much the tip of the icebergs. As you're about to find out, bases are not as basic as you thought. Little note up in the top left-hand corner, please can you revise ionic equations if you find this at all troubling, lesson at all troubling, because they are important in this topic, and you will find yourself falling behind if you don't. Okay, so here's what we're covering today. Only a couple of points. It's going to be quite a brief video, which I'm sure you're all a little bit upset about, but we're going to be moving on to much more complicated ideas that all fit in together a little bit later on, so it's better that we just make sure we've got the grounding really solid. Okay, let's first define what an acid and a base are. First guy one of the first people to try and define this was a bloke called Arrhenius. Here he is, with his wonderful attempt at a Movember. He said an acid is something that supplies hydrogen ions in aqueous solution, and a base is something that accepts hydrogen ions from aqueous solution. Simple. Seems kind of, straightforward. Now, Bronsted and Lowry. This is Bronsted's on the left. Is that Bronsted? No, that's Lowry. This is Lowry, and this is Bronsted. They both independently came up with the same idea that an acid is a species that donates a proton to another species in a reaction, and a base is a species that accepts a proton from an acid in a reaction. Now, this sounds almost identical in theory to the last one. However, there's a couple of things that are different. Firstly, the acid isn't donating the proton into solution, it's donating it to another species. There is a reaction happening. It is saying that every time a proton moves from something to something else, that is a reaction. And secondly, there's two species involved, so always having a reaction. Okay, so let's have a look at a few examples, and we're going to be doing some ionic equations here. So here's the classic example of a acid-base reaction. We've got sodium hydroxide, hydrochloric acid. They make sodium chloride and water. Salt plus water, classic reaction. So let's take out the spectator ions. So let's look at for them. Sodium, that's the same over here as over here. Let's get rid of that. Chloride, that's the same over here as it is over here. Not really done anything. Let's get rid of that. H and OH have combined to form H2O, which is something new. So that's going to be in our equation. I forgot to put the state symbol on this, but it should be there. So this is the ionic equation for it. H plus OH minus goes to H2O. The classic acid-base reaction. Let's look at a different one. Here we've got sodium carbonate and hydrochloric acid going to form sodium chloride, carbon dioxide, and water. Bit more complicated. It's a bit harder to see any species really taking hydrogen ions from solution. That's not what's happening. What's happening is the carbonate over here is taking two hydrogen ions and it's using them to split itself up into CO2 and H2O. We didn't really see that. You don't see that clearly until you get it into the ionic equation, which is why we use the ionic equation. Now, you should be covering equilibrium at the moment, and I'm sure some of the eagle-eyed among you may have been thinking, well, what about in an equilibrium? Because we have two reactions. We have one going forwards and one going backwards. Now, if we take this case where you could say I'm dissolving ammonia in water, but I'm going to say I'm reacting ammonia in water. In this case, we form the ammonium ion and the hydroxide ion. Okay, so ammonia has accepted a proton. That means it's a base. Therefore, water has acted as an acid to donate a proton to form OH minus. So going in this direction, this is a base and this is an acid. But we've got an equilibrium, so we can go in two different directions, and it's still going to be an acid-base reaction in this direction as well. So going in this direction, ammonium is an acid, it gives a proton to hydroxide, which accepts the proton. Now you may have noticed that I've coloured these two in red and these two in blue. That's because these two are linked and these two are linked. You can see that this one has got a nitrogen and 3 hydrogens, and so is this. This has also got 1 extra hydrogen, and this one's got an oxygen and a hydrogen, and then 1 extra hydrogen because it's an acid, and so is this. And these are called conjugate acid-base pairs. So a pair of the two that are linked are conjugate acid bases. So here we go. There's another one. Let's look at that in a little bit more detail. If we've got an equilibrium, both directions are going to have an acid-base reaction. Therefore, there's going to be acids and bases on each side, and there's going to be linked pairs called conjugate acid-base pairs. Let's have a look at a reaction you're probably familiar with, which is the reaction to form the precursor for nitration of benzene. We've got sulfuric acid over here, nitric acid over here, sulfuric acid that's lost a proton over here, and nitric acid that's gained a proton over here. Now, both of these two things are acids. Well, nitrous acid, sorry, nitric acid. No, it's nitrous acid. Both of these two things are called acids, but this one's acting as a base because it's accepting a proton. So going in this direction, we have acid 1 and base 2. I'm calling it base 2 because I've linked it up with acid 2, and acid 1 because it's linked up with base 1. So acid and a base. Then going backwards, the sulfate, the thing with the sulfate in it is now a base because it's accepting a proton from the other thing, which is now an acid. So you can see quite clearly there's a conjugate base pair, acid base pair between this one and this one, and a conjugate acid base pair between this one and this one. There will always be two, and in any equilibrium acid base reaction there will be conjugate acid base pairs. So we should be able to spot them. And to do that, you're going to need ionic equations. Okay, that's all for this week. Was a little bit of a short one. Hopefully you'll make notes, excellent notes, and we'll be ready for a practical on Friday. Thank you very much for listening.